Okay, so I think we'll start now. And today, in fact, we are learning part two of CNN, which is Convolution Neural Network theory class. So yesterday we covered part one, which was more about images and a lot of things about digital images, challenges in dealing with images, and what is convolution and what is pooling. That's what we learned yesterday. So today we'll get a bit advanced in CNN, and we'll get bit detail of we'll get into detail. So I'm Shailendra Kadre as usual, and I'll be the instructor for this course today. Okay, so welcome this Sunday evening, everyone. So we get started from here. Yesterday we left on class break one. So we start again here. I make it full screen. Yeah. Okay. So we saw that yesterday we saw that in an image, a digital representation of image, which is pixel, and each pixel is filled a number between 0 to 255. But if we normalize and divide every pixel by 255, then every pixel will be filled with a number between 0 and 1. So it can both be, it can either way, like filled with 0 to 55, 0 to 255, or any number between 0 and 1 if we normalize it. Now what happens, you see that in this figure, if you see here in the leftmost figure, in centrally there is a like 3 by 3 image, 3 pixel by 3 pixel image. And there is a 2 pixel by 2 pixel kernel or filter, whatever we call it. So when we convolve with this image with this filter, so there is likely that corner edges information may be lost actually. So some details, if there are more details towards the edges, then they may get lost. And we see that the image size also shrinks when we do convolution. So to maintain the image size and to read to properly capture the details on the edge, what we do something called padding. You see here, all around the image we have 0 0 0 0 one covering of 0 0 0 is there all along. So there is top, there is a row of 0, and it is all along, it is covered in a rectangle 0 0. So this extra layer of 0 0 what we put all around, it is called padding. So why we do padding? So padding means we have put an extra layer, so then that extra layer becomes the edge. And actual image is it's somewhere in center. So we are able to better capture the details in on the edges. They are not lost. And at the same time, you see that after convolution of this image, the original image size, the output image size also is 4 by 4. So if you want to maintain the image size and you want to capture the detail on the edges, you do this kind of padding. So this may give, like, you may have some questions about padding. Just hold on for a minute. So I'll take you here, something like here, like you just see here. I have an image here, 6 by 6 image on the left side, which is I am calling corner pixel. And I'm making a convolution with 3 by 3 filter. I'm making a convolution with 3 by 3 filter. Now let us see what happens. Like the cell which is the leftmost top corner, one cell is marked with A. So when I do convolution, A is covered only one time. After that, I will move kernel to the right side. Okay, A is covered one time. The column of A is covered one time, and after that, I move kernel right side. Now, whatever column is marked as B, like in the center, you see there is something marked as B, cell is marked as B. So if I am moving during convolution, if I am moving my kernel below, vertical direction, I am going down, below side. So you will see that B is covered three times, three movements. Like first convolution, it will be covered. Then we'll shift by one. We'll shift down by one cell. Then also B is covered, and then we shift one more cell. That three times B is covered. A is covered one time in full convolution operation. B is covered three times. And how many times this C is covered? You see center, we have marked C, something called C. So this C, if you count in a 6 by 6, if I do convolution, so it is C is covered 9 times. What does it mean? C is covered means center details, the details which are on center are getting covered more times. So that information we are covering more number of times, which is slightly below the edge we are covering say 2 times, and which is top corner we are covering only 1 time. What does it mean physically to us? It basically shows that model will work with pixel C very fine. Model with work with pixel C very fine. Why? We are covering it many times, so that details are captured well, and it will misinterpret the pixel A. It will means will may not be very correct word, but it may misinterpret pixel A. Why it may uncover? Because only in our convolution we are covering it only once. So that is why we do sometime something called as padding, which I shown you here. So if I do padding here like this, so the actual zero, or you see that the image is 3 by 3 image in the center, 3 by 3 image. So top left corner is 0. So that 0 will be covered more time because we have covered it with padding. So that way we are able to preserve the details which are there in the corner better. We are able to capture the information which is there in the corner better if we do this kind of padding with the help of convolution. And if we don't do padding and you see the image is simply like this, I'm covering A, or which is there on the top, A which is there on the top, I'm covering only 1 time. But if I do some kind of padding with 2 layers or 1 layer, that A will be covered more times. So I'm able to capture A multiple times, so that the details are captured better. Is it understood? Any questions on this? So Priyanka, you have joined new. I will explain you once again. You are there, Priyanka?
Yes, sir.
So we are telling we have started just 2 minutes before you came. So here is a 3 by 3 image in the center, if you see in the left side. So what I told that when you have something like this and you do convolution with a 2 by 2 filter, what happens? The corner details are not captured well. I'll tell you why they are not captured well. So corner details are not captured well. So to capture the corner details well, what we do, we cover it with a layer of 0, 0 on the all around. We give a padding of 0, 0 all around the image, which is shown here. So that way, our image size also gets bigger, or image size also gets preserved, and the corner details are getting captured better. So how it is? You see, this is a 6 by 6 image on the left side, corner pixel. The corner pixel, which is marked as A on the top left corner, it is during the entire convolution operation of 3 by 3 filter here, A will be covered only once. Now I have started moving kernel down, one cell down, one cell down. So you'll see that whatever I have marked B here, B cell with the name B, it will be covered thrice. And in the center I have marked C. In the entire convolution operation, C will be covered 9 times. So what does it mean? The topmost corner is getting only one time coverage. C center is getting more time coverage, and in between B is getting some little more time coverage. So what does it mean? It basically shows that the model will work fine with the pixel C because we are covering it many times. It is well covered, but it may misinterpret corner A. If there is more information towards the corner A, it may misinterpret it, because why? We have covered it only once. And when we do convolutions, we always miss some details. Actually, we capture only main details. Okay. So if we are doing B or C more number of times, so it is a better chance that we will cover them well. So that's why we do some kind of padding, which is nothing but covering image all alongside by one layer of zeros or maybe two layer of zeros. Like that we cover. That is called padding. This is a technique, simple image processing technique which we use while convolution. Any questions in this, anyone? So we go to anyone, any questions here? Priyanka, understood?
Yes, sir, understood.
Okay. So now we are getting a little bit into formulas now. So assume that you have an image of input size NW, NH by NH is the height, NW is the width in pixels. NH is the height, and NW is the width in pixels. You are covering it, you are convolving or covering it with a kernel of KH height and KW width. So what will be the height of, what will be the input size of output image? So output image will be this formula. NH minus KH plus 1 into NW minus KW plus 1. Now you apply to this particular example which I have given. So anyone wants to take a shot and apply this formula to input and kernel, this input and kernel which I have shown in the figure. Anyone wants to take a shot? Udesh?
Yeah, that's simply input has dimension 3 by 3,
Okay.
which means NH and NW becomes 3.
Okay.
And kernel size is 2 by 2. So KH and KW 2 by 2. If we put that into formula, we get output as 2 by 2. That
yeah,
is
very nice.
our
Very
output.
straight, simple. Yes, very simple arithmetic, right? So even one fourth grader or fifth grader can do it. So this is a very simple basic formula. So now we know if we have a image with some width and height, and we convolve it with the image of convolve with a kernel or a filter of some width and height, we know what will be the size of output image. That basic formula we have it. And now we have tested it. Anybody, Shailesh, any questions here in this particular small operation? Any question on this?
No, I think okay.
Anybody else, any questions on this side? Okay. So now same thing like I'm showing once again. So in center you see an image which is slightly whitish. Actually, you see a little more bright. There is an image of 4 by 4 pixels, 4 pixel by 4 pixel. We have all around we have given a padding of 1. Padding of 1 means all around it is covered with 1 0. So now you see how the filter behaves. The filter is shown here in the blue. Filter is 2 by 2. So first it is kept in the topmost corner. Then we shift it 1 cell right. 1 cell right or 2 cell right. So when we do this shifting, so 1 cell or 2 cell, that is called stride, S-T-R-I-D-E. Stride X means stride in X direction. Stride Y means vertically down. Stride in Y direction. So these two terms I am introducing here. Stride means simply whatever cells we shift, that is stride. So if we shift by 1 cell, that means more number of filter will be required to cover the entire image. So image will be captured well, more fine details will be captured. If instead of one cell, if I shift by 2 cells, I will need less number of filters to cover the same image. But at the same time, the disadvantage will be that coverage of less number of details will be covered because we are jumping to 2 cells. Okay, so it depends on how coarse or how fine image we want, output image we want after convolution. We decide our stride based on that. If we want to capture very fine details, then we keep our stride as only 1. If we want to capture only very coarse details, then we keep stride as 2. So see, if it is jungle, we just want to differentiate between one tree and one face. So we don't need very fine details, okay? So just a coarse details also you capture and then you feed into a ANN, it will classify into whether it is a tree or a face. So you don't need a lot of fine details there. So in such cases, you will keep stride as 2. So this is the concept of stride. Very simple. Stride can be in 2 directions, X direction, stride X, Y direction, stride Y. So both stride X and stride Y are required to cover the image entirely. Now, I want to take you to a simple, very simple maths here. Consider this little bit, be careful here. So what I have done is here n by n pixel by n pixel image I have, and I have covered it all around with a padding of P. This P can be either 1 or 2. Padding like that, 2 layers of zeros or 1 layer of 0 or 3 layer of 0. So padding is P all around. Then filter is there f by f. F width, f height filter is f by f filter. And we are convolving the image with padding, whatever we have done. So like this we are convolving. With padding we have done. So like this we are doing convolution and covering the entire image. So once I do the padding, it is very clear that the size of the image will become n plus 2p by n plus 2p. 2p, clear? Why 2p? Because p padding on one side, p padding on one side. So both height and width of the image will get added by 2p. So size of the image will become 2p by n plus 2p plus n plus 2p. It is getting convolved with the image, with a filter of f by 2f. Okay. So you see, now this formula will come. And suppose, first you see equation 1 which I have marked in the left hand side. Suppose I convolve a image of n by n with a filter f by f. We have just seen the formula. The output image will be n by f plus 1, n by n minus f plus 1, n minus f plus 1. We have just seen formula here, right? This formula we have seen. Same formula is the equation 1. Now we have done the padding 2p on padding pp on all the sides. So the size of image will become n by 2p and n by 2p. So formula equation 1 will get modified to n plus 2p minus f plus 1, n plus 2p minus f plus 1. So that will be the size of output image. Now what we want? We don't want the image after convolution, right hand side of the right hand side of the equal to sign. The convolved image, we want the same dimension as the original image. So you see the equation n, equation 3. So what we do, n plus 2p minus f plus 1 is equal to n we put, because we want same size. You solve this equation, you get p is equal to f minus 1 by 2. Simple arithmetic you do, little bit algebraic here and there, left and right, you will get p is equal to f minus 1 by 2. P is nothing but padding, f is nothing but filter size, f minus 1 by 2. So it clearly shows that padding depends on the dimension of the filter. Okay. So this is a simple use case I have taken, wherein an image of n by n with padding p all around, if it is convolved with the image of with a filter of f by f, and you want to get the same output size as n by n, what will be the size of padding? So padding will be f minus 1 by 2. Padding will be f minus 1 by 2. Any challenge in this actually? You might feel that it is little involved, but it is simple algebra of 6th class. Anybody, any challenge here?
My
No
question
challenge,
is,
but my question is, would stride also not play a role here?
Madam, stride we are not talking about right now.
Okay.
We are assuming stride as 1 here.
Okay.
Okay. With stride, I will take you another formula is there. I will show you that formula.
oh, actually, I have one question. So basic, yesterday what we studied is, I think convolution is used for the dimensional reduction, right? To simplify the image and all. But here, n by n is again getting converted into n by n.
Why we are not reducing size of the image? Because our image is special in this case. We might have more details on the edges, which we don't want to lose. So even after convolution, we want some, there is some use case, say if age, there are more details towards the age. So convolved image also, you want the same size of input image. So that this is the special use case, this is the special use case which we are discussing here, wherein input image and convolved image are of the same size.
Oh.
Okay. So to make that, what kind of some padding will be required? Some padding will be required. Without padding, you cannot do, because without padding, if you do n by n image with f by f filter, it will become n minus f plus 1, n minus f1. It will shrink. But if you want that image should not shrink, then you have to give padding. So what is the size of padding required? That's what we are calculating here. So size of padding required will be f minus 1 by 2. Understood? Is this understood?
Yeah, that is understood. But only question is, basic purpose of convolution was to simplify the thing. But here, even if I go to the previous slide, then the basic characteristic is not changed, right? All the things are just scaled outer parameters where 0 is
See,
0.
if you do n by n image with f by f filter, it will reduce in size, right? It will reduce in size.
Yeah.
So there is chance that you will lose some details in the corner edges. You want to preserve the size of image after convolution. So you have to give padding. So how much padding will be required? So that padding will be p is equal to f minus 1 by 2. That is the size of padding which will be required to conserve the size of image after convolution.
Okay.
So this is a special case where we want to give more importance to the details which are there towards the edges of the image.
Okay.
Understood? Now see here, I explained to you here that if something there on the edge, you are covering it less. So you may lose, mathematically you are covering it less means physically what you are doing. Physically you may lose some details on the edge. So to avoid that, you are covering padding. So if you give the padding, the size of convolved image will become more. But if you want to keep it same, n by n to n by n, input also n by n, convolved also n by n, then size of padding required will be p is equal to f minus 1 by 2.
Okay.
It's a simple use case, a special case, which is what we are discussing here.
Okay.
Now, here a simple I have shown, there is a red filter here, the red filter, a simple filter shown, 4x4 filter on a 8x8 image. So one stride is equal to 1 is shown and stride is equal to 2 also shown, just to make it more explicit and you understand what is stride of 1 and what is the stride of 2. It's very simple. There is no brainer in that. Now, what is the stride in CNN we have seen? The larger stride means fewer neurons in the next layer, which translate to the fewer calculations in the less memory usage. Understood, na? If we do stride 1, memory usage will be X. And if I give a stride of 2, calculations will be less. So memory required to keep, do the same convolution will be less. Memory requirement will be less. But at the same time, my image, which is convolved image, will not be as fine as stride is equal to 1. So stride is equal to 2, I am getting a coarse image, and stride is equal to 1, I am getting a fine image. But advantage with stride is equal to 2 is that I am using less memory. So it depends on your use case whether you want to use a stride equal to 1 or 2. So both advantages and disadvantages are there. Nowadays, some people use larger stride in convolution layer to get rid of pooling operation. Means RISE are not using pooling layer. They are using more stride of 2, stride of 3 they are using, and they are reducing the side of image. Now here there is a equation of 4x4 image. This is a 4x4 image. We are doing a stride of 2. So it will become a image of 2x2. So you are interested in formula now, right? So this is the formula. So Shrutika madam, W by W is the size of input image, F by F is the size of filter, P is the padding all around, S is the stride. Stride can be 1 or 2, and this is the formula to get output image size. Is this understood? Very simple formula. We are not getting into derivation of that. Actually, a derivation of this is there, but we are not getting into derivation of this. I am directly showing you the formula. The output size W out is equal to W minus F plus 2P by S plus 1. So this is a simple formula to get output image size, which depends on stride here. Okay, understood? Shailesh, Shrutika madam, Malini madam. Udesh?
Yes, sir, understood.
Yes, yes.
Any questions here?
Yes, sir, understood.
See, there is a derivation of this. But I don't want to confuse you yourself with the derivation. I don't want to confuse myself also with the derivation. We are concerned with the formula, and this is the simple formula. W by W input size, F by F is the size of a filter, padding is P all around, padding can be 1, 2, 3, and S is the stride. Stride can be 1, 2, 3. So you just put here simple value thing and get the output of the image. So this anyway, this will be shared with you, or this slide will be shared with you. So all these things given, you can always calculate the size of the image. Okay. Now I'm getting into something a little more details of CNN. So we have an input layer first, and then we have convolution layer. Convolution pooling 1 combination, convolution pooling 2 combination, then we have a fully connected. So see what is there in the fully convolution layer, what is there in the, what are the constituents, like what makes a full convolution layer. So you have a convolution layer first with the filters, okay, that you have. Then you have something called batch normalization layer, batch normalization. You have something called batch normalization. Then you have a ReLU layer. We'll see each one of these in detail. There is a ReLU layer. There is a ReLU layer. And after that, you have a pooling layer. Same. This is a convolution, batch norm, ReLU, and pooling one. This is one particular bunch or a set that you keep on repeating many number of times. So if you want to repeat, then you will repeat again. Convolution 2, again batch normalization, ReLU, and pooling 2. So ReLU is what? ReLU is nothing but the activation function. So we'll in the next, in like coming slides, we'll see why we are using ReLU and why we are using batch normalization. Okay. And after that, you have a simple ANN. You put whatever features you get after convolution 2, you get a set of features. You feed into fully connected layers. Fully connected layers is nothing but your simple ANN. And you can then put output. You can have either 1 neuron or 3 neurons or 5 neurons, depending upon whatever classes you have. If it is a binary problem, in output layer you put you put sigmoid function as the activation function, and if there are multiple classes like 3, 4, 5, then you put softmax as the output function. Okay, and why we take softmax, why we take sigmoid, so we'll cover in some later lecture where we are covering advanced topics in CNN. So right now, let us assume that if it is binary classification, we'll take softmax in the output layer, and if it is multi-class classification, we'll take softmax. And all the convolution layer, there will be only one. Activation function, which is ReLU. And why we'll take ReLU and not anything else, that we'll see in the later slides. Okay, so this is what is the general structure of any CNN. Now I want to tell you a little bit about filters, like what kind of Shailesh, you are asking some question about filters that time.
Yeah.
So I will tell you something more about filters today. So, okay. So Shrutika madam, I think your video is there and your full face is not coming. So either you want to make it complete, or you just mute your video, whatever you want. So now I'm giving you a simple filter. Now I'm starting something with filters. Okay. So there is a dog image, you want to blur it out. Blur it out means you want less details. Don't want full details, blur it out. So you will use this kind of filter, 1/9, it can be 1/6 or 1/10 or 1/12 or 1/13, whatever. But the similar filter you will use to convolve the image of dog. It will become something little blur or what is there on the right hand side, little blurring. So you want to make blur, blurring means what? You are removing some details, right? You are removing some details. You are reducing the memory usage. You are reducing the memory usage, right? So blurring, that is blurring. So for blurring, you will use something similar filter. Then reverse, you want to do sharp, you want to sharpen the image. So left hand side is a blur image. Right hand side you see little hair and all those little sharp image. So something like that filter will be there. So you see plus is filled up. All the corner are zeros and plus is filled up. It is symmetric. -1, 5, -1, -1, 5, -1. This kind of filter will be used for sharpening. Then you see detection of Sobel filter, edge detection. So this filter, if I apply this filter, left hand side is the image, dog image. If I apply horizontal and vertical, these two filters are there. If I apply these kind of filters, then the convolved image will become something like this. It will be only edge detection. Edge detection will be done by this kind of filter. See what it is. So horizontal edge detection means only top and bottom rows are filled up. Middle it is empty. Vertical edge detection means vertical column, left and the rightmost column is filled up. Middle one is empty. So Nilesh, Shailesh, you are interested in horizontal and vertical edge detection, right? So if you apply both this filter to this dog image, it will become something like this.
Okay.
But still it is, you can recognize it is a dog, right? Is it not enough to recognize a dog? When it is enough to recognize a dog, why you don't, we want a complete image with all the details. Why you want that? Because your aim is to just classify dog, cat or lion or tiger. That's what you want to classify. So why you need a complete image of the dog? You are unnecessarily wasting memory and processing power of the computer. Just convolve it with these filters and make it simply like that edge. And this edge with whatever edge in this from edge image, whatever features you are getting, just feed it to your ANN. It will be easily able to classify whether it is a cow, dog, cat, tiger, or a horse, or whatever you are feeding. You don't need a complete image, right? So then again, one filter I am showing you here to vertical edge detection. So this is the image. Simple image is shown on the below. See, small image in smaller size image is shown with the help of arrows. So image, these edges are to be detected, and the same image is shown in the form of matrix, the pixel matrix. Filter is also shown. So it is 1, -1 on the edges, and in between it all is filled with 0. You convolve, you will get something like this on the right hand side. So that is nothing but vertical edge detection. That is vertical edge detection. Then some more filter I want to show. You have this kind of some blocks, engineering blocks are there. You want to detect horizontal images. So you just put this filter 1, -1, 1, 1, 0, 0, 0, -1, -1, -1. If you convolve the left hand side image with this filter, you will get something similar to right hand side. All horizontal edges are getting detected. So this is just to give you a feel of filters. Now some real life images I'm showing you. Like a car is going on a highway. I do it with horizontal edge detection. Horizontal edge detection means some filter like this 1, 1, 1, 0, 0, 0, -1. Like I do convolution like this. So I'll get image something like this. Because all images are curved here. There is nothing much defined horizontal or vertical. So something like this is coming. If I convolve with the edge of vertical filter I give. Vertical filter means something like this 1, 1, 1 column 0, 0, 0 and -1 like that. If you filter I give, then you will see something like this. Some details of the car are seen. Like this it will become. So it is I'm giving a real life example. Okay. Now these are about filters. So in this, there is no exam here, but from exam point of view, if you want to see only how to detect horizontal edge and how to detect vertical edge, these filters are what you can remember. There are very complicated filters like I shown here to sharpen the image, to blur the image. And there are 100 more types of images with different cell filled up with different values. So I don't think you can remember all this. So these simple filters, if you remember, you will get a feel how convolution takes place and what happens after the convolution to the image. So this is enough for a conceptual knowledge. Rest all is left to the computer. Whatever it does, it does. Okay. So filters, anybody, any questions? Because these are the some filters I've shown you to give you a feel, nothing more than that. Okay. So that's what was about filters. Any questions about the filter? I'll take a minute break here. Any question about filters?
So this
You will anyway get this.
filters are not computationally costly, no? That is just a matrix multiplication and summation, right?
Yeah, but see, if you have this kind of image, a dog image, how many features you will have in this?
Cells will be more.
And compare it with the right-hand side image, which is just of edges. So which one will take less memory and less computing power, right? Right one, definitely the right one is easier to process, right?
Yes.
And if there are millions of images like this, and you are simplifying like this, like simplifying by convolution, so you are saving a lot of computation as well as memory, right? Yeah. That's what we want in. That's what is our aim in image processing, right? Yeah. And if image size is bigger, you imagine how many details it will have.
Another thing what I thought was in computer vision, if you're using it for a self-driving car, then the image will keep changing every second.
Yeah, madam, it is very challenging problem.
So, computationally, it has to be very
efficient.
Image,
it has to be very efficient because your car will not have a supercomputer.
Correct. So anything that is computationally less intensive is preferable.
Yeah, every second, I think you will be taking, your camera will be taking either 20 frames per second, and if it is more precise, it will be taking 40 to 60 frames per second. So that many images it has to process per second. So you see how much efficient your CNN should be, how much efficient your computation should be. So imagine those kind of computations are very complex engineering, madam. It is not only CNN architecture. Lot of engineering which goes behind that, parallel computing and all those kind of things, memory management. Lot of engineering is involved, which goes for such a faster and real-time processing. It is not only CNN which is important. Sorry, lot of engineering aspects are involved. So that is one thing. Now we get into little more detail. So we are getting into a new concept, which is called feature maps. I talked about feature maps many times, but I never explained you what it is. So now it is our time to take a dig at what are feature maps. So feature maps means there is one image. You are convolving it one filter. So you will get an output image, convolved image, which is output image. So that is called one single feature map. And I'm telling you, like, I'm telling you, in a single image, to capture all the details, you never do convolution with one filter. But usually 32 filters, 62 filters, 128 filters, like that you use number of filters to capture different details. Some filter will detect horizontal edge, some filter will detect vertical edge, some filter will detect eyes, nose, like that. Different filters, different parts of the image will be picked up by different filters. So if you have, say, 32 filters, your convolution operation on a single image will run 32 times. So you will get 32 convolved images, right? 32 convolved images you will get. So each convolved image is called a feature map. Simple. There are 32 filters. I am doing convolution 32 times. So my output also I will have 32 convolved images. So each one that convolved images I am calling as feature map. So feature maps after the convolution are equal to the number of filters we are applying. Each one filter, one feature map. One filter, one feature map. Understood? So in short, if you can want to call it short, convolved image we are calling as feature map. See here, simple. I am keeping it simple. One image, say it is 4 and 7 by 7 image, 7 by 7 image, and done convolution with 3 by 3 filter. I am getting one feature map. Simple formula. One convolution image, one filter is one feature map. Now here what I am doing, one image is there, black and white image is there on the one monochrome image is there, but 28 by 28 height, 28 pixel height, 28 pixel width. Single channels. Why single channel? Because it is black and white, single channel. I am convolving it with 6 filters. You see here 6 filters are shown. Different color filters are shown. So I am taking 6 filters. Each filter size is 5 by 5. 5 width, 5 height. And depth 1. Why depth 1? Because it is a single channel filter we are using. So depth 1. Okay, so 6 filter we are using. So how many feature maps we'll get? We'll get 6 feature maps, which are shown on the right hand side. It is a very confusing concept, but I have made it very simple for you. Even I was confused when I learned CNN first time. What is feature map? How many we get it? So I made it very simple for you. Count the number of filters you are doing. Same will be the number of your feature maps. Understood? This image is understood. So filter 6 feature maps you are getting. Now note down the size of feature maps. Feature map size here shown is 28 by 28. 28 by 28 because maybe in the original image they might have used some kind of padding. Some kind of padding is usually used. So you might have used some kind of padding. So that's why convolved image and input image size is same. But thing to note here is there are 6 filters I have used. So feature maps also 6. So feature map is nothing but a flat figure, a rectangle or a square. Feature map is a rectangle or a square, 2 by 2. Like 9 means it is having height and width, only 2-dimension figure. That is what is feature map. One feature map is either a rectangle or a square. It is having height and width, 2-dimension. Feature map is always 2-dimension. So that is what it is. And like color image, we are taking here a color image. So image itself will have 3 channels, which are shown here in the 3 depth. 3 depth means 3 channels. So what happens when we when we do convolution for a color image, we have 3 channels in the color image, RGB. So convolution happens for each of the 3 layers. So even our filter is also have depth 3. So I have shown here 6 filters of 5 by 5 into 3. Into 3, why? Each of filter is having 3 channels. Why 3 channels? Because each RGB, there should be one channel. So 6 filters, each filter is having 3 layers. Why 3 layers? RGB. So output. But you see, output is not having 3 channels. Output feature map will be only 2D. Output feature map will be 2D. Our image was 3D. Our channel filter was 3D, but output image is always, output filter is always 2D. Filter is always 2D. That is what to remember. But still, you use the 6 3D filters, 6 3D filter, so you will get 6 feature maps. But feature maps will be always 2D. That is what you have to remember. So this is a very concept. And this feature map, then we feed into a ANN, which is a fully connected layers. And then we classify into 2 class, 3 class, 4 class, whatever it is. So our convolution plus pooling gives you feature maps. So feature maps look like this. They are always the 2D objects. One feature map is a 2D object. So see, this is the same thing I am showing here once again. How many feature maps? It is clear to you. It is clear all. Now I want to show you Like I'm telling you, you feed a feature map into a ANN, like fully connected layer. So your feature map is always 2D, but your ANN needs a single dimension output, single dimension input, right? We know that in ANN, we put a column vector or a row vector in a ANN. Say in the ANN, we always give single dimension output. So what we do, every two dimension feature, we do some kind of flattening operation called flattening. So see how flattening is done here. So this first row is 110, second row is 421, and third row in the feature map is 021. So see how flattening is done. First is 110 flattening, then second 421, then 021. Very simple. We are keeping one column like one row below one. We are just flattening it, making a rectangle into a straight line. Understood? Flattening, anybody, any challenge? Everybody understood how flattening is done? Shubha, understood how flattening is done? Concepts are very simple, but you should know the concept. That's it. Flattening is very simple. Malin madam, Shrutika madam, Shailesh, understood?
Yes, sir.
Yes, sir.
Very simple concept, but you should understand what is flattening. Otherwise, lifelong you will be confused what is flattening. That's why I have given a simple figure. A 2D feature map is there, pulled after pulling 2D feature map, and I'm flattening it. Why flattening it? Because our fully connected layer or ANN, what we call it, it needs a column vector, single dimension vector it needs. So 2D vector we have reduced to single vector. 2D vector we have reduced to a single dimension vector. That's what it is. Then again, I'm showing you a basic structure of a CNN. I think we are almost done with CNN. Input, there is input image. It may be single channel, 3 channel. But in MRI, there are 60 channels, 70 channels also may be there in the image. 3 channels is for simplification. It may have 70 channels also in MRI images. I'll show you one example. That is feed to one input convolution layer. Then that convolution layer itself will have a ReLU activation function. ReLU activation function is shown here. I think when we discussed ANN, we discussed in detail what is a ReLU function. Then we do pulling, then we do flattening, and after flattening, we feed into a fully connected layer. And then at the output, we have either a softmax or a sigmoid. So this is the basic structure. I'm once again showing ReLU function. So it looks like for value negative values, 0 and for 0 and all negative values, the output will be 0. But for all positive values, the output will be X, whatever is X. This is the ReLU function. We discussed this in detail. Anybody, any challenge, they can ask question about ReLU function. Equation is on the left hand side, and it looks like this. ReLU function we have already discussed. So this is the concept of ReLU, and then we go ahead. Why we use, I promised I will explain you why we use only ReLU function. So it is used to avoid one problem, something called vanishing gradient problem in deep neural network. Vanishing gradient problem means when we do back propagation, there is some kind of gradient being calculated, like there is a loss function is there, like y actual minus y predicted whole square we take, right? We take it for every point, which is the loss function. Then the gradient of loss function is calculated for each and every parameter of the deep learning each and every parameter of the neural network. We calculate its gradient. So what are the parameter? Weights and biases. For every weight and every bias, we calculate the gradient. And that gradient we propagate backward means from output layer to input layer. Backward, from output layer to input, we calculate, propagate it, and we, with the help of that gradient, we update the weights and biases. But there is some problem called vanishing gradient problem, which I'm not telling you in detail at the moment. So you assume something called vanishing gradient problem means, so suppose there are 20 layers in your head, 20 hidden layers. 20 hidden layers in your ANN. While doing back propagation, your gradient will become 0, or it will become so small that weight updation will not take place. At the 10th layer, your gradient will become either 0 or it will become very small, 0.000001. So your weights will not get updated at all. Weight will not change. Weight will not get updated. So this is a common problem in deep neural network, which is called vanishing gradient problem, which is a serious problem. But that means back propagation process is failing. How it is failing? Back propagation gradient should travel up till input layer from output layer. But gradient is vanishing, means it is becoming 0 or near to 0, somewhere in between only. So after that, backwards, going backwards, your weights and biases will not get updated. But if your weights and biases are not getting updated, what is the purpose of training? Training is failing. So this is your training will fail because your weights and biases remain unchanged because of vanishing gradient. So we'll see this in more detail in advanced topics when we'll discuss we'll take a separate class on advanced topics. So that time we'll discuss this vanishing problem in more detail. So to avoid the problem of vanishing vanishing gradients, we use this ReLU function. And after a lot of research, researchers have found out that ReLU function is something which can be used to avoid the problem of vanishing gradients. Researchers have found it out. And so we are empirically using it because researchers have recommended us to use ReLU function in the hidden layers, in the convolution layer, because it avoids the problem of vanishing gradients. Okay. So this is the advantage, that we avoid the problem of vanishing in gradient. So what is the disadvantage? So ReLU can be fragile during the training. A large gradient flowing through it can update it in such a way that the neuron will never get further updated. A large gradient flowing through the ReLU function can update it in such a way that neuron will never get further updated. However, we can work with this by setting proper learning rate. So con is that with larger gradients it misbehaves with ReLU function, and further updates may not take place. We are not going too much into detail because these are very deep research problems. But understand there is a advantage is that it avoids vanishing gradient problem. Disadvantage is that for if gradient value is very large, there it may happen that further upgradation of that neuron or ReLU doesn't take place. So we can avoid this problem by using proper learning rate in the neural network. So learning rate is nothing but a very sensitive hyperparameter in the case of a neural network. So that if we adjust properly, then we can avoid this. What is the disadvantage or con of the neural network that ReLU we can avoid, and at the same time we can have the advantage of using ReLU. ReLU advantage is that it avoids vanishing gradient. Now, if you are confused, it's okay. If you are not understood, it's okay. These are very deep research problems, and if you don't understand at this stage, you leave it and go ahead. Just live with it and go ahead. Assume that there is something called vanishing gradient, and ReLU avoids that. So that's why in convolution layer we have to always use ReLU. But as you mature with the CNN and deep neural networks, these problems will be definitely clear to you at a later stage. But for beginners, even if you don't understand, don't mind, it's okay. But remember that for every convolution layer, we are going to use only ReLU function and not anything else. And the reasons I have explained, if you not understood, okay. Later stage, when you get more matured with the ANN and all, you will get automatic insight into this. Okay. So now I am coming once again I am reminding you the structure of CNN. There is input, there are convolution. After convolution, we get feature maps. If you have 32 filters, then we will get 32 feature maps. We do pooling. So for each feature map, there are 32 feature maps after convolution. So there will be 32 feature map after pooling also. Once we get the feature map, we'll do something flattening. After flattening, we'll feed into deep fully connected layer. And after that, we'll have the layer of fully connected layers and then final output layer. So that is what is the mechanism of CNN. And one thing you have to remember, in neural network, there is nothing small or big. Now you are learning as a beginner, you are learning only neural network with 2 or 3 layers, 2 convolution, 2 pooling, 2 convolution, 2 pooling, like that. But next moment you have to learn with a neural network or CNN with 60 layers. Like that also you have to do. So there is nothing big and there is nothing small neural network, there is nothing big neural network. As a beginner also, you should be prepared to work with a bigger neural network, because all computation is being done by computer, and you should understand the concept. So next I'm taking you into little big, I'm not getting into this details. Then it's a complex neural network.
I have a question on this actually.
Yeah, tell me.
ANN, whatever means convolution pooling, okay. But what is the, because in ANN we studied regression and classification, right? So in this case, what is the type of ANN we are using? Classification?
CNN is always a recognition type of task. That is classification.
Okay.
And ANN can be regression or classification both. But CNN is always recognition only. So recognition is nothing but classification, right? Whether it is Shailesh Kadre, or whether it is Shailendra Kadre, or whether it is Uddesh Soman. Seeing face, you have to classify, right? So now I'll take not more than 10 more minutes. I'll finish. Once again, I'm reminding you the structure of CNN: input, image, you do convolution, you do pooling. Again, you may do convolution, you then pooling. Means pooling output is fed to our next convolution layer as the input of the convolution. Means output of the first pooling layer will go as an input to the next convolution layer. Then pooling again will take. Then I may put 2, 3 more such layers. 2, 3 more. So my question is, natural question you will ask, how complex can it get? How complex can it get? So I will show you one complex, very classic, very complex but very classic standard neural network structure, which is called VGG16. VGG16. It was discovered, it was designed by, invented by Oxford University somewhere not too far, like 2-3 years back only. It is the very, say maybe 14, 15, maximum 4-5 years back. It was devised by Oxford University. So it is a very famous or very standard architecture we use for image classification. Okay, so what is this? We prepared. It is looks something like this. Very complex. Input image, color image you input. First 3 layers you see, just see the image. Don't get into the detail. See, these are the details here. Input, convolution 1, convolution 2, then pooling. Then again convolution 2, convolution 2, pooling. Then again 3 layers of convolution, then again pooling. Then again 3 convolution layer, then again pooling. Then again 3 convolution layer, then again pooling. Then 3 dense layer. And basically after that you have output layer. Okay. So it is University of Oxford designed it, very complex neural network, but it is not very common. It is not the most complex neural network, most complex CNN available. It is one of the complex neural networks. It was designed in 2014. After that, many more sophisticated such CNNs have been proposed that will learn in during when we learn in transfer learning. That time we'll learn that. Many more sophisticated have come. And whatever accuracy is being given by VGG16, they have improved it by like 5-6%, 7%. They have improved the accuracy further. So it was the origin of 2014. So if you have to learn one complex neural CNN, so it is the most basic complex CNN to learn. See how. So now you will ask me how many how many convolution I can put at a time, how many pooling I can put, how many sets of convolution pooling I can put. So Shailendra Kadre will tell, boss, there is no rule. It's a art. Whatever works, whatever gives you best accuracy, go on pooling, and whatever computing resources you have. Based on that, you put all this, do the experiment, and declare that I am getting a 98% accuracy. And if I put one more convolution layer, I'm getting 99% accuracy. There is no rule to how many layers of convolution, how many layers of pooling you put. So that's what we are going to discuss. Then convolution layers, pooling layers. So why number of convolution and pooling layer we took? So basic convolution neural can be seen as a sequence of convolution layer and pooling layer. So that's what we see here, right? Sequence of convolution and pooling. Okay. When image goes through them, important features are kept in convolution layers. Like each set of convolution layer extract a type of features. Each convolution layer, type of convolution layer, extract one type of features. Thanks to the pooling layers, these features are intensified and kept over the network, while discarding all the information doesn't make a difference for the task. Means the convolution layer will make a feature map. Pooling layer, what it will do? Pooling layer will intensify it, further intensify it, reduce the dimension, and all extra or the unnecessary detail it will reject. Now that pooling, whatever pooling output you get, you feed again into a convolution layer. Same thing keeps on repeating. So what convolution layer does? It extracts a type of features and pooling intensifies it. Intensifies it means it keeps the max pooling we are doing. Max means in particular cell we are taking the max value. Max value we are taking means only the prominent feature we are taking. All the rest other details are getting rejected, and we are reducing the dimensions. Okay, so this is what convolution and pooling. So intuition behind multiple convolution layers in a network. Okay. So first convolution layer of the CNN is essentially standard image filter plus ReLU. The goal is to take basic features. First layer, first convolution layer, the first block here, first block 2, convolution 1, convolution 1, 2, and pooling. First block, what it will do? First block will extract the basic features, edges, corners, most basic features it will detect. Now, second convolution layer. Second convolution layer means convolution 2, 1, convolution 2, 2, and pooling. Second layer, second set. What it will do? It will do, instead of raw image, it will accept feature extracted by the first, of course, because it is sitting after first convolution block. So whatever output is given by first convolution pooling block, that goes as input to the second block. So it allows to combine basic shapes into more complex features. Like your edges and basic features are extracted by the first layer convolution layer. Second convolution of layers, more complex features. More complex features. The features extracted become more and more complex as we go further down the network. Like your first block is extracting most basic features, simple edges, vertical edges, horizontal edges. More complex features like curve and all, or nose or ear or something is getting extracted in the second block. Third block is extracting more abstract features, more complex features. Like that it progresses. As we go towards the right, more and more complex features are getting extracted. That's why we put multiple blocks of convolution and pooling. That is what is the science. And once again, I'm showing the VGG16 in a more sophisticated image. And I think number of filters. I think this you need not go. And neurons in dense layer alpha, we have done it already. So once again, batch normalization. So why we do batch normalization? Batch normalization is the layer that allows every layer of the neural to do more independently. So batch normalization allows each layer to learn more independently. It avoids overfitting also. Batch normalization is something equivalent to your standard normal or min-max scalar is there. No? Min-max scalar or standard scalar. We have two types of scalars in 2-3 types of scalars in scalar. Min-max scalar or standard scalar. So batch normalization. Regularization, yeah. So batch normalization is something equivalent of that in neural networks. Okay. So batch normalization, number one, it allows every layer to learn independently. Number two, you want to remember batch normalization is helpful in avoiding overfitting. Okay. So need not go into much detail right now. Two things you remember. It allows every layer to learn more independently. Number one. Number two, it is useful to avoid overfitting. Just now remember when we discuss advanced topics in the towards the end of this course, that time it will be more clear to you that how exactly batch normalization and what exactly happens when we do batch normalization, what exactly happens, and why it is used. So that time more detail we'll discuss that. That's why I have kept it in the advanced topics. Otherwise, everything if I explain now, it will be too much jumbling. Right now, we are learning only the high level details. Only high level details we are learning. All the low level and more details we will learn in the advanced topic. That time, you will have some idea of CNN also. That time, you will be familiar with ANN, CNN, RNN. So, your familiarity will be more. So, that time, more intricate details or more complex details that will be easy for you to learn at the later stage. That's why I have kept it in the advanced topics. Now optimizers. So optimizer, I think it is same in ANN and CNN. So optimizer tries to lower the means optimizer is for your ADAM optimizer or whatever optimizer you use. It is for back propagation we use it. So why we use optimizer? An optimizer tries to lower the loss function by updating the model parameter in response to the output of the loss function, thereby helping to reach global minima with lowest loss and more accurate output. Means what? See, this curve I have shown here, like here, there are two peaks to this curve. One is local minima, one is global minima. So our aim is to minimize the loss function. So loss function is what? Y actual minus Y predicted whole square. Sigma. Sigma means done for all the points. So that is what is our objective function. So we minimize it. And when we minimize it, what is our aim? Whatever is the curve being formed, that we want to reach the global minimum of that. So optimizers helps us to reach that with the minimum number of iterations. So optimizer helps us to reach global minima with minimum number of iterations. So that is what is optimizer. And generally we use ADAM optimizer. Like there are so many kind of optimizers we have: gradient descent, stochastic, ADA-grad, ADA delta, RMS prop, ADAM. So generally we always start by using ADAM only. We start with ADAM, and if we are not getting good results with ADAM, then we'll try other ones. But by default, any kind of problem, we'll start with ADAM optimizer only. And now, what are these optimizers? What is ADAM? What is RM prop? What is ADA delta? What is ADA grad? What is stochastic gradient? And what is gradient descent? So gradient descent, I think if you learn a little bit depth, your linear regression, you know what is gradient descent. But other optimizers, I think it's a kind of, I'll be very open with you, it's a deep mathematics. And for the sake of like to keep the course easy, I will keep it out of the scope of for this course, because I will not get into mathematics of ADAM, RM prop, ADA grad, whatever it is. So we will use it because we are told to use ADAM. We are told to use ADAM, that's why we'll use it. And we'll not get into mathematical details of these optimizers. It's a very deep mathematics. And some detail, some more detail about optimizers, I will provide you in advanced topics when we'll discuss towards the end of this course. That time I will give you a little more detail of details of these optimizers, but mathematical functions of that optimizer and the whole gradient wave propagation problem is involved mathematics, and I'm not going to get into more details of that in this course. And it is not required also if you are only a user of ANN or CNN. You learn what is the concept, but you need not go get into mathematics if you want. But if you want to go and research on those fields, you want to research deep, then you must know the mathematics behind all these optimizers. You must know the mathematics behind full back propagation process. But research is not the aim for this course. I want to make you ready for the industry. That is what the aim for this course. And for that aim, we need to learn only the concept. The deep mathematics behind these concepts is not necessary in my opinion. But if you are interested, I think a simple internet search will give you all the mathematical details about ADAM, ADA grade, or ADA delta, or RMS crop, whatever you just put in the internet, you will get more details. So you are most welcome to study on your own. But deep mathematics behind these optimizers will be out of scope for this course. So I think this we have multiple times we have repeated VGG 16. So what is the conclusion? Last slide. Convolutional neural network is a popular deep learning technique for current visual recognition task. Means it is a very popular default network for visual recognition task. Like all deep learning techniques, CNS is very dependent on size and quality of the training data. Quality and size of the training data is very important. Sometimes to train networks which I have shown here in the left hand side, to train the network of this size, you need millions and millions of images which are not available with many people. So some people, what they do, whatever images are available on the internet, full internet images they download, and with that they train their networks. And such trainings with very advanced GPUs takes 4 weeks, 5 weeks, 6 weeks, maybe more than that. So that kind of resources are available only with very big companies like Microsoft, Google, and Amazon, and those kind of companies. We will never have access to such GPUs and sub computer systems unless we work for those companies. So this VG16 and all are trained on very advanced supercomputers and all. So we have to use it as it is because they have pre-trained. We are using pre-trained network. We cannot train it in our say Google Colab Pro, or we cannot train it in our local machine. They are trained in very advanced supercomputer. We'll be using as just like as it is. We'll be using them. We'll be using them. And sometimes what we'll do, we'll not do the complete training also. Last output layer or last 2-3 layers we'll remove. We'll train only last 2-3 layers. We'll not train the complete network. For the complete network, whatever trained weights and biases have come from Oxford or whatever their companies like Google will keep the same weights as same because training has already happened. But to suit to our problem, only last 2-3 layers will remove and train it to suit our problem. So that is called something transfer learning. Why transfer learning? Because VG16 or Google Net or whatever is the big network, training has already happened. So some knowledge has already been important in the model. What we'll see to if that class has 1000 models and our problem has only 3 models, what we'll do? We'll remove the output layer of that. We'll remove the output layer because their output layer 1000 classes are there. Our problem only 3 classes. So we'll remove their output layer, put our own output layer with only 3 neurons and retrain only with that network. Or maybe 1 or 2 fully connected layer will retrain. Rest all the weights will keep the same. So that is the concept of transfer learning, and it is knowledge transfer, right? Because training has already happened in Google, Oxford University. All the training has already happened. Training has already happened means weights and biases have already been updated. We are using the same weights and biases. Only last 2-3 layers we are retraining it for our specific problem. So that we can do on our machine, Google Colab Pro and all that. But full network training of this size we can never do on this kind of our kind of system. So we have to reuse whatever they have done. And lastly, this question I think came when we started our neural network. I want to repeat it. Given a well-prepared data set, listen carefully. Given a well-prepared data set, CNNs are capable of surpassing humans at visual recognition tasks. Understood? Like humans have, computers have surpassed, they have defeated world grandmasters in chess. World grandmasters in chess have been defeated by like world grandmaster is defeated by computer program, right? So even the same fashion, CNNs in some cases have proven better than human eyes or human brain. So that already has been done. But for that, what you need a well-prepared data set and a well-architectured CNN model. It has already surpassed your whatever human judgment it is there. So I think Shrutika madam or Malini madam asked this question, right? So I think you have answered now. So CNN have already surpassed the judgment of human beings if provided you have well-prepared data set. By well-prepared means you should have millions of such images to train. You should have a well designed CNN network, and you should have a nice bigger supercomputer at your disposal to train your neural network. If you have all these things, CNN can surpass the human judgment. That's what is the conclusion. And with this, I think I will finish. Congratulations.